Nearly there, and it's official. Looks like we can get started. Welcome back, everyone. We're now in week 15, so last instructional week until finals week. And seems like a big week going on, but I just couldn't hide a lot of these files inside an assignment because we're getting to the point where for our last sections, 6.2, 6.3, I can't actually assign an assignment on these because that assignment would be due in finals week. So instead, I have suggested exercises for the material we're going to look through today. I have the suggested exercises as a PDF if you have a slightly different edition of the textbook, as well as the solutions for those exercises for both section 6.2 and 6.3. We made some good headway into section 6.2, and 6.3 is a pretty short section. So that's going to be our work today. When we come back next class on Thursday, we'll be all caught up with the material of the course and just be doing review problems for the last amount of our time. Other things going on in the announcements are I do have a block of extra credit opportunities. I wanted to get to section 6.4, but I'm going to blame this on the fire alarm that we had at the start of the semester. There's just not enough time to really get to that problem. But for students who are curious about what's going on in here, we'll actually talk a little bit about it in section 6.3 because it leads into the Gram-Schmidt orthogonality process. And if you decide to take a look at those examples, I'll post solutions here. There'll be an extra credit opportunity. One last problem on the final exam will be a section 6.4 problem. So if you have the extra time and resources, this would be a good extra credit to go for. Your final exam score can't exceed 100%, but any work you do on this problem here is just extra insurance on the final exam. So this is a good opportunity to go for, especially if you're already caught up on homework. If you go a little bit beyond where we are doing today, 6.3, it would be rewarding on the final exam. The other extra credit opportunity is relative to the final exam itself. I feel like this is more just kind of a statement of fairness. Everyone sometimes has a rough exam in a math class, but if, say, exam 2 is your rough exam, but you learned those topics well and came back strong on the final exam when those topics came up again, then the way the extra credit works is the minimum grade among exam 1, 2, and 3 can be replaced by the final exam grade if that final exam grade is higher, so that I'm not hurting anyone's scores. This will only help for the course. So it's kind of like an extra credit opportunity with the idea of fairness baked in. If you relearn that material on a hard exam, this final exam can bring it back up. And this last bit right here is not exactly an extra credit opportunity, but in a way it kind of is. If you got behind on any section in this homework, even if it was, say, section 1.3 weeks and weeks ago, well over 10 weeks ago, then if you turn this into me, sooner is definitely better to help you prepare for the exam. But the final due date to turn it in would be on Friday, December 19th. I'll accept all graded work at that point and include it in your grade to improve your score. So, well, that's the announcements at the moment with the extra credit opportunities and what we'll be doing today. Any questions so far, folks, before we go to the next block of announcements? Okay, well, for the other part of the announcements, this is what we'll be doing on Thursday. I have a set of final exam review problems in this document here that we'll be taking a look into. We'll solve as many of them as possible in our 75-minute window that we'll have. And anything that do not get solved, I'll post the full solutions afterwards so that they'll be available here. Then scrolling down even further, our final exam is a weird one. It's going to be on Friday. Most of the exams I've given have been on Mondays and Tuesdays. So this is definitely a weird time block. It's officially on Friday and we had some corrections on this, 10 a.m. to noon, 12 p.m. It'll be in this classroom if you're in the in-person section. And I sent instructions for Pocatello testing centers, Idaho Fall testing centers, if you're in the online section. Well, it'll be just like the regular exams, 1, 2, and 3. They'll show up in the same places they've done before, whether it's a testing center or the classroom. Only difference is, well, it's a weird time and it's a 2-hour exam. Well, any last questions at all, folks, about the final exam at the moment? Okay, we'll talk more about the final exam as we're going through the review when we start that on Thursday's class. So for what we have going on today, we're going to be finishing up the course material, returning to section 6.2. And again, 6.3, it really could have been rolled into 6.2. There's only two examples on this set of notes. And it's a logical extension of what we're doing in this section, because these are just suggested problems. Also drop hints as we do go through the notes that so-and-so problem is what you can expect to do on the real final exam. Because there's no homework on these sections, I feel like massive hints are a great idea for the last couple sections we're getting through. So here's where we left off. We have a concept of an orthogonal basis, a set of vectors that are pairwise orthogonal. Their dot products come out as zeros, are considered to be forming an orthogonal basis if the zero vector is not a member of that set. So we did one of the fastest basis problems of all time, not even doing a determinant on this. 3 dot products giving us 0 told us v1, v2, 3 were mutually orthogonal to each other. That means it forms a basis, and our work was done here. So orthogonal vectors suddenly start to look pretty useful. Another really fast problem was this one right here. If we have an orthogonal basis of vectors that are non-zero because we said they're a basis, then for any vector y, we can rewrite as a linear combination of these basis vectors in a particularly strange kind of way. The scalars in that linear combination are these dot products. So we took those dot products that you see here, y dot u1 is a numerator, u1 dot u1 is a denominator, forms 26/18. And to re-express y as a linear combination of vectors in an orthogonal basis, this was all you had to do. Looks like a little bit more work on this page, but this was kind of a nasty problem to do by scratch with row reduction. So the orthogonal basis gave us yet another interesting tool. But the notes didn't really resolve last class when we were looking into this is where in the world did this come from? Sure, orthogonality is part of the secret here, but there's some motivation on where this structure really comes from. So that's what the next part of the notes is going to get into. And then we'll start resolving questions about distances from a vector to some subspace. So that's kind of our warm up for what we did last Thursday. Any questions or comments at the moment before we take a look into the next concepts? Okay, so now we're going to investigate what is that thing? Where does it come from? Why are we computing these and why are they so useful? And that's what example 4 is all about. It's asking us to rewrite a vector y, -4, 1. So we're working in R2 as a sum of y equals y hat plus z. Y hat is a multiple of the vector u that's provided as well. And z is orthogonal to u. So z dot u has to come out as 0. So we're going to deconstruct y as a multiple of u, which would mean it's in the subspace of span u if it's a multiple of it. And as another vector z, where z is orthogonal to u. In other words, the vector z is inside the orthogonal complement of u as well, so, or rather the orthogonal complement of span u. So when we come up with y hat, you might have seen this object before in a calculus setting. This is the orthogonal projection of a vector y onto a vector u, or we could say onto the span of that vector u at the same time. Z is the component of the vector y that's orthogonal to u. And, well, the way we can kind of compute this is sort of fun in a way. It's really just deconstructing the big asks of the whole problem. Y hat is a multiple of u, so let's just rewrite what that means in linear algebra sense. Y hat is a multiple of u, very literally means y hat is some scalar alpha times u. If we can come up with that scalar alpha, then that's, well, half the problem. We'll know how to get the right multiple of u. The next part is that z has to be orthogonal to u. In terms of what we did in the last section, orthogonality would mean this. Z is orthogonal to U implies Z dot U has to come out as the zero scalar. So no vector symbol on there. That's what we mean by orthogonality. This doesn't seem like a lot to work with, but you know, there's also an equation. Z is not just orthogonal to U, it's also represented in this way. Z, if we solve for it to where it is at the red dot, could be rewritten as Z equals Y minus Y hat. So just subtract Y hat from this equation and you get Z. So putting all this together, I don't know why I switched to black on that. Let's keep that in blue. Hang on, colors are hard today. Back to blue, Y minus Y hat. Putting that all together, we can start now finally making substitutions on this process. In place of where Z is, put in Y minus Y hat, dot product with U. There's a distributability property with the dot product over real numbers. We can distribute the dot product through and get Y dot U minus Y hat dot U is now equal to the zero vector. And then we can make another substitution because we have a statement for Y hat. Y hat is alpha U. So putting in that substitution, we have Y dot U minus alpha U dot U. Other properties of dot products tells us we don't really have to put any parentheses here because whether you did the scalar multiplication first or did the dot product first, you get the same exact value. So this is unambiguous without parentheses. This is set equal to 0. And now, well, this is an equation, a scalar equation for which you could solve for alpha on this scalar equation. And that would tell you exactly what multiple you have to take. So let's do the heavy work of solving for alpha. Not too bad. We have Y dot U is now equal to alpha U dot U. Solve for alpha by just dividing by U dot U, and we get that this whole thing, alpha, is equal to Y dot U divide by U dot U. And that's that same weird scalar that we saw in the very last theorem. Let's take a peek. It's this thing. This just showed up for our particular vector U. So that's where this stuff is really coming from. And it requires us to have an orthogonal basis if there is more than one vector U in consideration. Here, there's only one vector U. So as long as it's not the zero vector, this is a great formula. So we know what alpha is. We know what Y hat is at this point. Y hat equals Y dot U. Let me put that in blue just to show the substitution. Y dot U over U dot U, rescaling U. So every vector can be decomposed in this kind of way. Here's the part that's a scalar multiple of U, and Z, we already knew what that was by subtraction. Z is going to be the part that's orthogonal to the vector U as well. All we have to do is just run through the formulas, but we've kind of done this in the last section. We've seen that structure before. So this is essentially the end of the derivation, and now we're just going to compute these objects. Any questions at the moment, folks? Tracing through any of this logic? Okay, let's compute some stuff. How about the dot products first? Y dot U over U dot U. Here's our vector Y, our vector U. So Y dot U is going to give us -4 plus 2. Denominator is U dot U, so that's going to be 1 plus 4. That's the length of U squared. So this is altogether -2/5 of U. So it comes out as, rescale this by -2/5, and we have, oh, hang on. I put in a vector U there. Should probably put it in here as well. Let's call this Y hat. Sorry, for some reason I was going to focus on this scalar part, but then I slipped in the vector U. If you put in the vector U, you're looking at the entirety of Y hat. So I snuck that in and put Y hat on the left. Looks like we're just computing the whole thing. We're about there. So multiply this by -2/5, and we get -2/5 here. Let me fix that. And then finally, -4/5 here. So that's our vector, y hat. So it's supposed to be a multiple of u, but it definitely is. The multiple is -2/5. We literally took it there. The big check in all this work is when we go to calculate z, is it really going to be orthogonal to u? So there's a fast check there. Next step is let's calculate z. Z equals y minus the vector y hat we just calculated. So the vector y, rewriting it so in terms of denominators of 5, comes out as -20/5, 5/5, minus, here's the vector y, -2/5, -4/5. It's kind of a negative sign hell, but if we're careful with this, we'll get through it. So our vector z is now going to come out as, let's see, it's -25 plus 2/5, so 18/5 on that vector. This is 5/5 plus 9/5, excuse me, plus 4/5 for a 9/5. Oh, thank you for that negative sign there. So drop the negative on that one. There we go. Can just barely accommodate that. Thanks for spotting that. So -18/5 and 9/5. This is a good point to just kind of pause and reflect. Let's see if z is really orthogonal to u, because we claimed that's what it's supposed to do. We even wrote down the dot product. It's 0. So let's check that out. Here's the vector u, z down below. Z dot u is going to come out as -18/5 plus 9/5 times 2 is 18/5. With that negative sign correction, this comes out exactly as what we want it to, exactly 0. So do we do the problem? Let's see. Rewrite the vector as a sum. Really, we kind of did, because we know the y hat, we know the z. But the big punchline is the original vector y can now be rewritten as this part. The projection onto the subspace L, where L is going to be the span of u of the vector y. So that's just -2/5, -4/5. Y is inside the span of u, plus another vector. This vector is the component that's orthogonal to u. In other words, different way to say that is that z is in the orthogonal complement of L, which was span of u itself. So it is -18/5, 9/5. I know it's not harmful to do another check on this, but if we subtracted right over here, that check is not as major as the dot product check. But let's just double check anyways. That's -20/5, so that would be a -4. -4/5 plus 9/5 is 5/5. So it gives us the 1. So we did some weird stuff. We did an orthogonal projection of y onto a vector u, or we can visualize it onto an entire subspace, span u. We found the component of y that's also orthogonal to the subspace L, span u, or you could say it's an orthogonal complement. But all this is purely algebraic, and even though these are important equations and concepts, it's really hard to get a visual of what did we just calculate. And so the next problem is less the calculations in algebra, and it's all about how would you visualize all this stuff in R2. Any questions before we take a look at the visualization side of this? Okay, so what does it mean to project onto a subspace L some vector y is what this problem is all about. First, the theorem is the roundup, the formulas that we just derived ourselves. So if u is a non-zero vector in Rn, and y is some other vector in Rn, could be R2 or R20, we can decompose y in this way, y hat plus z. So y hat is a projection on a subspace L of the vector y. Z is the component that's orthogonal to U, or you could say it's in the orthogonal complement, L perpendicular, where L is span of U. And the key to doing all of that is just this particular dot product. And then Z is just Y minus Y hat, which comes naturally from this equation here. So that equation is not the big one. It's more about that scalar, Y dot U over U dot U, is what's making all of this work right here, getting those two different vectors. So this problem is less about actually computing this and more just about the visualization. The instructions say, sketch and label the vectors and subspaces labeled below on the same set of x1, x2 axes. And this is the problem that I'm going to ask on the real final exam. I feel like a good visualization problem is pretty helpful to tie these concepts together. So expect this type of problem on the final. I'm not going to ask too many questions from 6.2, 6.3, because 6.3 is essentially 6.2 at higher dimensions. This will be one of the two questions I'll ask. So this question doesn't even require you to calculate anything. If you can visualize where things go, that's good enough for me. And I wrote in an emphasis on the final exam. You don't actually have to calculate these. It's all about the visualization. I also gave some scratch paper, so let's treat ourselves to some of that. The picture is just not going to look right unless we have some really good scratch paper going, some balanced axes. It's a bit too large. Okay, that should do the job. So let's go for that sketch. I did make a change here. This was 2, but I felt like the sketch got a little too busy unless I moved the vector y, this component here, a little bit further out. No, actually, now that I think about it, I think it'd look better at like a 2,4. Let me change that one more time. Sorry for going back and forth on this one. Let's make this a 4,2. I think that picture will come out a little bit cleaner. So we're going to sketch and label the vectors and subspaces z, w, y hat to z, and w perpendicular, but they go together in a certain way. So z is going to go together with the orthogonal complement of w, u and w go together, as well as y hat itself. So really to start this all off, let's start by plotting the vector u. The vector u is -4, 3. So let's go -4 up 3. And here's where the vector u lies. So that takes care of the vector itself. It's also a visualization problem. We need to sketch what does the span of u actually look like in the R2 plane. That's just a line that goes through the zero vector. Recall the span is a subspace, so it has to contain the zero vector. It also has to contain u. U is inside the span. So those 2 points give us the line. Here is w equals span of u. So we have 2 things down. We can't put y hat down just yet until we know where is y itself. So with a bit of a modification, just to make the plot cleaner, here's y, 4 over 2 high, and that's the original vector y. But now that we can see it, we can compute y hat if we really wanted to, but this is all about just sketching these. How do you get y hat? Well, it's the orthogonal projection of y onto u, or the span of u is another way to say it, which means an orthogonal projection means if we drop a vertical going this way at 90 degrees, the vector that would be here is that orthogonal projection. Geometrically, that's what we're meaning when we're doing this computation here, getting that object. So visually, just literally project down, try to get it right at 90 degrees. Doesn't have to be perfect, it has to be in the right ballpark. And this is our vector y hat, right? Triangle here, or the box just indicates that this is at 90 degrees. So that's where y hat comes into play. So that one's done. Now we just need the component of y that's orthogonal to u and the orthogonal complement w perp. Well, any questions at the moment, folks? Getting that value there? Okay, I think sometimes this one's a little bit easier to plot because if you write down a one-dimensional subspace like this, and you're asking to put down this thing, this is the orthogonal complement we looked into in the last section. Every vector inside of W perp by the red dot has to be orthogonal to the vectors in span U. So it makes sense that it should look like this. The orthogonal complement should be another subspace coming out at another 90-degree angle. That was my visual attempt at 90 degrees. Let me try once more. That'll do the job. Let's just make that dot a little bit bigger. And here's the orthogonal complement. This is actually span Z, where Z is the component of Y, orthogonal to the subspace W. And once you have this down, if you project Y going this way, landing right here, that's Z. In other words, there's a vector Z right here, but we need our vector to connect with the initial point at the origin. So once you just slide this all the way over so that the y hat goes into the origin, this point y goes into the subspace W perpendicular, you have Z right at that spot. So graphing W perp gives you Z at the same exact time. So we did it. This is the decomposition. Y is equal to y hat plus Z. And in this decomposition, we have a vector inside the span of U, and we have another vector Z, which is orthogonal to U at the same exact time. So visually what we did on paper, all of this stuff right here, really just looks like this. Slightly different grid for each different choice of vector U and vector Y. And again, this is a real final exam question, just different vectors. If you could see how to plot these kinds of things, then you'll be in great shape. So it's really just the geometric intuition about what's going on with this theorem. We'll use this theorem a couple more times, but this is just our moment to pause and reflect. This is supposed to be geometry of vector spaces, so we should have a sketch somewhere, and this is it. Any questions about this at the moment? Okay, we can make some interesting reflections now that we've computed all this visually. You can make the statement that if you ever wanted to find the distance from, say, some random vector y, like this one, to some subspace, say this one, span U, the distance from the vector y to a subspace span U is just that length right there. So if you can calculate that distance, you've got it. But that distance right here to here is the same as this distance. So the distance from the vector y to some subspace is just the length of, or the norm of, the component that's orthogonal to U in the very first place, just Z. That's kind of a cool reflection. And what the section 6.3 is all about is an extension where W doesn't have to be a one-dimensional subspace like we see here. It can in fact be dimension 2, 3, 4, 5, any dimension whatsoever. And this is our notion of distance from a vector to a subspace. We try to find the best approximation vector, or the closest vector inside span of U to the original vector y. But in doing so, you just construct Z and you find its length. So that's what the next couple problems are going to be all about. Here's the same theorem, just recopied again for easy reference. And we're going to do exactly that process that we mentioned. Compute the distance from some vector y to the line through U equals 1, 2 in the origin. Well, this is just a different way of saying compute the distance to a subspace. The line through a vector U in the origin, this is just a fancy way to say, let's call it L, equals span of u. So to do that, all we really need is to find z. First, we find the closest vector inside a span u. That's the orthogonal projection of y onto u itself. So in that picture we were just looking into, that's what y hat was. Let's compute that part first. Y hat is going to be the projection of this random vector y given to us onto the subspace L. So we write it out this way, projection onto the subspace of the vector y. But it's just this particular formula once again. We compute y dot u over u dot u, rescaling u. So here's u, here's the vector y on the right-hand side. Let's do the numerator first, y dot u. That's going to be -3 plus 18. The denominator, u dot u, is going to be 1 plus 4. This rescales u, placing it inside the span of u. So we have altogether 15/5. It's kind of nice to get round numbers. So this is 3 times u. So back to this vector, scaling by 3 gives us -9. And let me try again on that one. 3 times 9 is 27. So here's y hat, that first orthogonal projection. Next thing we're going to need is the component of y orthogonal to u. It's going to be the vector z in the orthogonal complement of L, but finding that length of that vector.
I'm curious, why did you scale y instead of u?
Well, that's a great question. It should have been the u I was scaling. Thanks for mentioning that, Brian. So I had u here, but I think I was just looking into the wrong spot there. That's going to make a big difference in our work. So thanks to that correction there by Brian, let me take 3 times the actual vector u, and we get 3, 6. Okay, that saved us a lot of trouble. Thanks again for mentioning that. Other questions or comments so far? Okay, now with that correction, that looks a little bit more reasonable numbers as well. Finding the vector z is just finding this vector right here. Computing the length is giving us the distance. So now we're nearly at our target, finding that particular distance. But the next step is compute z. It's got the nice formula, just y minus the vector we just calculated, y hat. So go y minus y hat, and we'll get z is equal to -3, 9 for the vector y, minus 1 y hat, which is 3, 6, is going to give us a new vector. That's going to be -6, +3. So that's the component of the original vector y that's orthogonal to the vector u. So this vector z is in L orthogonal. Let's double check that. So take z dot product u, we'll get -6 plus 6. It is 0, so that correction again saved us. That's a good mid check right there, just the dot product. Z really is orthogonal to u, so it really is in its orthogonal complement, L perpendicular. And now we're done. We can say distance from y to a vector z, or let's say this better, distance from y to the line through u equals 1, 2 in the origin. The distance from y to L is the better way to say that, is going to be equal to the norm of z, which is pretty fast to calculate. Take z dot z, square root the result. We'll get that component squared, 36 plus 9. So it comes out as a square root of 45. And this class, as far as the numbers go, if you just stop right there, that's completely fine with me, because I'm most concerned with the linear algebra, and right at that step, the linear algebra ends. But you could reduce this as 9 times 5, so it's really 3 root 5. You could get a decimal approximation, but I'm not too concerned about all that stuff. If you ended on just root 45, and honestly, if the numbers are uglier and you ended just right here, I would have given full credit for stopping at this point. It's just arithmetic here on out. And if this is the right value, then that's good enough for me. I know everyone can simplify if we need to, or approximate if we need to, but sometimes these numbers get ugly. So sometimes this is a good stopping point, even right here. We did it, folks. We can now take the distance between a vector and a one-dimensional subspace, say span of one vector. The next section is really just doing more of this, and only difference is higher dimensional. But before we go to that next section, I think I have one more problem we'll do on here. So let's take a look into that. It's really the same problem, but we have some formal definitions finally being given. It's really the same form as before, but it's all about the distance being emphasized now. So if we have a non-zero vector u, and let L be the subspace, L is span u, pick any other vector y in Rn, we can calculate the distance from y to that subspace L by doing the same work. Distance from y to y hat is going to be just the length of y minus y hat, but that's the definition of z. Z is y minus y hat. So really all the formulas we saw in these notes was more just about doing that part right there and seeing what kind of new things we can do with that, whether it's checking for a quick linear combination or computing distances. So let's give this another try just for the sake of practice. L is going to be span u. U is defined right here. And that's this part of the formula right here. First thing we want to do is calculate y hat. So y hat is going to be y dot the vector u over u dot u, rescaling u. This is in a higher space, R3, but still the subspace is dimension 1. So really the same kind of problem, just harder to visualize. Take 5 here, multiply -1 for y dot u. Down the line, we'll get -5 minus 1 plus 4. Then u dot u is kind of nice. This is just 1 plus 1 plus 1. Rescaling u, so we've got a -6 plus 4 for a -2. Divide by 3, slightly inconvenient. Rescaling u, which is -1, 1, 1. So altogether, this is positive 2/3, minus 2/3, minus 2/3. And we're essentially a third of the way through the process. Next thing we need to calculate is the vector z. Z is just y minus y hat. So this is kind of the major step right here, using that formula. Feels like I'm color coding everything, but it really splits into green and blue, where blue is now the component that's orthogonal to the subspace L. So z is fast, it's just going to be y minus y hat we just computed. So this is going to come out as, first the vector y, we should write it in terms of thirds. So 15/3 minus 3/3, 12/3, subtract 2/3, -2/3, -2/3. Here's the vector we'll get out of all of this. So let me know if I flip any negative signs. 15/3 minus 2/3 is 13/3. -3/3 plus 2/3 is -1/3. And 12/3 plus 2/3 is 14/3. And that would do the job. So now that we got down here, we need to find the length of this vector, which feels really tedious because, I mean, you have to square each components and sum them together. But you know, we can simplify this just a hair. Factor out a scalar 1/3 at this step, and it makes sense. You get 13, -1, and 14. Finding the norm of this vector is slightly easier because you just take the absolute value of a third times the length of that vector. So we're now at the end problem. Find the distance from y to the subspace L. In notation, this is distance y to L. Written out in that kind of way. But the entire punchline is this is simply the length, or you could say the norm of the vector z, the orthogonal component. And doing this norm as fast as possible, you would take the absolute value of 1/3, Then you have to multiply it by the square root of that vector dot product with itself. So 13 squared plus 1 plus 14 squared. And if you ended right here on a real final exam, again, that's completely fine with me. This is just arithmetic from here on out. Anything you do from here beyond, I don't think I would take off any points. So if you stopped here, I would just say you probably were a little short on time, and that would be a reasonable thing to do. If you have the time, take 1/1/3 times the square root of, throw this into the calculator. 13 squared plus -1 squared, or just plus 1. I think I ruined it. There we go. Plus 1 plus 14 squared comes out as 366. I looked into this earlier. This is 2 times 3 times 61, and 61 is prime, so the root is reduced. If you approximate it, that would be fine as well. But really, when I'm going to grade these, I'm looking right here. If it's all perfect to this step, because you got the right vector z, you'd get full credit on that line. But now it seems like a kind of a cool parlor trick. We can find the distance between a vector y, a random one, and some other random subspace. If you've taken statistics, this y hat might seem kind of suggestive to you. Sometimes y hat is a predicted value. It's a result of a regression analysis. And that's part of what chapter 6 is getting into. These are regression analysis techniques, the thing that works under the hood for those kinds of topics in statistics. And the book itself, if we had, say, a couple more weeks, maybe 3 more weeks to be safe, we could actually do statistics, regression analysis using these tools. Well, we're done with section 6.2, which means we're almost done with the whole course. Next section is just a slight extension, 2 more problems to take a look into, and we'll be done for the day. Any last questions whatsoever before we go to that last topic? Okay, let's open up section 6.3 next. And section 6.3, because this connects so strongly to section 6.2, what I've done on the very first page is just recopied this important theorem that we've been using, that we derived and we've used in several different ways, and the graphic behind it, so a random scenario. So if you take some random vector y, that's this vector here in black, you can decompose it into a y hat. This is the vector projection of y onto the subspace L. It's the best approximation to y using vectors inside of this subspace. You can also decompose it going this opposite way as a vector z. Z is inside the orthogonal complement, which is the span of z. Finding the length of this vector gives you a distance. And so the major goal of this entire section of notes is redo this all over again, but make L higher dimensional. Maybe it's dimension 2 or dimension 3 and so on. That sounds really tedious, but I think you'll like the way this goes. It's kind of a miraculous formula. This is the dimension 1 case. If we go to dimension 2, you put subscripts U1s on these, and the next one, the next term, will look exactly like this, but with subscripts U2 everywhere. So you just add more terms that look exactly like that, more orthogonal components, and you'll have the right vector y hat. It's a lot harder to visualize when you go from, say, a 1-dimensional subspace L to a 2-dimensional. So I let the textbook do the heavy lifting for us. This is what it looks like. And this is one of the very, very big theorems, the first one in chapter 6, the orthogonal decomposition theorem. It's the same theorem we were looking into, but it's been extended. If W is of dimension 2, we use those 2 terms. If W is of dimension P, if this is an orthogonal basis with P vectors for dimension P, then you have P different components that you add up in this way. All of these together makes up a y hat, and Z is computed through the same exact formula. So everything we did in section 6.2 was really theorem 8, but in the case that the dimension was 1, only one vector inside of this basis right here. So y hat still gets called the orthogonal projection of y onto w. And here's the visual. Here's a random vector y. Here's w, kind of indicating it's, say, dimension 2, or it could be higher dimension. If you drop a perpendicular down, we get the orthogonal projection y hat. And this entire formula right here is that formula for y hat. Then, same as before, take y minus y hat to compute the vector z. This is going to be in the orthogonal complement. Looks like it'd be one-dimensional if we're really working in R3. If you're saying R5 and W is two-dimensional, then W perpendicular would just be three-dimensional. Dimensions have to add up back to the overall vector space we're working in. So it's kind of a cool theorem because it's powerful. You can now compute a distance from a random vector y to some subspace. It has loads of applications. We've mentioned regression analysis quite a bit in statistics, and this is the big topic about it. And it's not too hard to use. It just looks like a humongous statement. So first thing we're going to do is look into a random set of two vectors, u1, u2, and a third y. And if this is all going to really work the way we hope, we need that, an orthogonal basis of w. So that's where we're going to start. See if we really have that orthogonal basis. If we didn't, we were probably in big trouble. This problem went sideways. But the cool thing about this problem is that it's really, really fast to check. u1 and u2, we already are going to say w is the span of u1, u2. So kind of like this wc right here. Next check we do is u1 dot u2 is going to be 0. Minus 1 plus 1 comes out as 0. We already know the vectors are linearly independent, so they will form a basis for w, span of u1, u2. But once the dot product comes out of 0, it's not just a basis, it's an orthogonal basis. So that's our big conclusion. Those vectors u1, u2 are orthogonal to each other. They make an angle of 90 degrees in the plane. So u1 comma u2 is an orthogonal basis. That means we have met the hypothesis of this theorem. We have an orthogonal basis, then just pick any vector y. We have a random vector y as well, and we can re-express it in this way. This is the vector projection onto the subspace W of our random second or third vector y that's provided. So that's what we're going to calculate next in part B. Determine the orthogonal projection of y onto W. We're going for that y hat next. And let me see if I can show the formulas at the same time. Here are the formulas, but we've essentially used this theorem a whole bunch already so far today. We are just using two terms now specifically. So y hat is y dot u1 over u1 dot u1, rescaling u1 plus y dot u2 over u2 dot u2, rescaling u2. Now we're done with this entire part of the theorem. So coming down back down here, we're going to take y dot u1 over u1 dot u1. So I'm just going to compute the coefficients first. So we'll have from here to here in the numerator, 0 minus 4 plus 1. Then u1 dot u1 is going to be 16 plus 1 plus 1. So this becomes negative 3/18 for a negative 1/6. Sort of inconvenient, but we'll work with the fractions as we get them. So far on the left, we have y hat is negative 1/6 of u1. And then we just do it all over again, focusing on u2 next. So let's focus on getting that scalar first. Y dot u2 over u2 dot u2. So now I'm focusing on this u2 and this vector y. Dot product between the two in the numerator is going to be 0 plus 4 plus 1. U2 dot u2 in the denominator is 0 plus 1 plus 1. So this one comes out as a 5/2. Let me double check my numbers. So 4, 1 for a 5. Okay. Kind of inconvenient, so more fractions. So plus 5/2 u2. Well, we've got y hat, but the next step, we have to come up with z. And so the most amount of simplification you can do here is very, very well worth the effort. It's also inconvenient because fractions are everywhere. Some of these problems are actually genuinely hard to rig to make fractions impossible, so it's sort of part of life. Here's one way to kind of maneuver through this. If we can get rid of the denominator first, then that would make everything a little bit easier. So let's make that one have a denominator of 6 as well. It's negative 1/6 u1 plus 15/6 u2. Now let's factor out a sixth and just deal with that later. We'll have negative u1 plus u2. That's not so bad. So negative u1, let me just write these in so I don't get tripped up on the negative signs by a 4, 1, negative 1. And that should have been plus 15 u2. Let me correct that work there. Plus 15 u2 left over from that 15 numerator. So 15 u2 is going to be plus 0, 15, 15. So this is altogether 1/6 of 4, 14, 14, doing the vector addition. Now we could divide these by 6 and get here 4/6 reduces to a 2/3. 14/6 reduces to a 7/3. And then again, 14/6 for 7/3 again. Kind of a nasty little vector there, but in higher dimensions, sometimes this is not too uncommon. So here's our projection y hat. Essentially, we found that piece right there on the graphic for the theorem. Next thing we want to find is the vector z. Same exact formula as before, so just y, whatever the vector was, minus y hat, the one we just computed, gives us the component in the orthogonal complement of w. So let me hide that part next. Now we're doing the decomposition, but first, to make any of that happen, we have to get the vector z. So let's rewrite z equals y minus y hat. That means z is going to be equal to, let's grab that original vector y, writing it out with thirds to get 0, 12/3, 3/3, minus vector y hat, which is 2/3. Oh, I switched colors there. Let me try again. 2/3, 7/3, 7/3. So altogether, it looks like we're getting a negative 2/3. Then 12/3 minus 7/3 is going to give us a 5/3. 3/3 minus 7/3 is going to give us a negative 4/3. And we can check all of our numbers, but here's the gold standard for the check. Z is in the orthogonal complement of W. And the last notes showed us how to really check that out. We don't have to work too hard. We just have to check that Z dot U1 is 0 and dot U2 is also 0. So let's do a really fast margin check. Z dot U1 is going to be, look way down here for Z, way over here for U1. We're going to get 8/3 minus 5/3 minus 4/3. That doesn't look too convenient. Oh, I might have a mistake on the number somewhere on here because this is not 0. It's close. We get negative 1/3 from that altogether. So somewhere here in the numbers is a buried arithmetic error of some kind. Let me see where that could have came from. So I did negative U1. That's 4, 1, 1. or 4, 1, negative 1. 15u2 is 0, 15, 15. We're adding them together, so that should have been a 4, 14, 14. So we got the 14 14s. And then divide by 6. 4/3 is 2/3. 7/3 and 7/3. That part looked all right. And then what did I do next?
I
Put this
think it's because when you did the 4, 1, negative 1, 0, 15, 16, and you added them together, it should have come out as 4, 16, 14.
Oh, I see that now. Yeah, that mistake right there was invisible to me. I read over like that one twice already. Thanks for spotting that. That's super helpful. So making the numbers come out right, here's this 16. Then 16, 6 comes out as a 8/3. Down here, this is now 16, or excuse me, an 8/3. Let me highlight these mistakes. That should have been 16 here. So 8/3 here, 8/3 here. And then this one should come out as 4/3. That's looking convenient because if you have a 4 right here, 4/3 minus 4/3 plus 8/3, that does in fact give us a 0. Phew, thanks for spotting that one. That saves us a load of trouble. Now let's check z.u2. Just because it works on 1 doesn't mean it's really in the orthogonal complement of w. Dot product with this one should come out as 0 as well. That's a little bit faster to check. We would have gotten 0 plus 4/3 minus 4/3, and it's 0 as well. So we have verified z is in fact in the orthogonal complement of w, because w span u1, u2, and the dot product against both of those comes out as 0. And the work is done on this. It says decompose y into this particular sum, y hat plus z. Really, that's just going back to what this decomposition is promising. You can decompose y into those two particular vectors, the orthogonal projection and the component orthogonal to w. So this problem is a little bit weird because it ends on the decomposition. We can say, therefore, y equals, it's going to be y hat first, which is 2/3, 8/3, 7/3, plus the vector z, which is negative 2/3, 4/3, negative 4/3. Let's double check that vector y. We should have be getting 0, 4, 1. And yeah, if you add across these, you get 0 in the first component, 12/3 is 4, 7/3 minus 4/3 is 3/3, giving us back the 1. So the vector y wasn't special. Any vector y can give you this decomposition. Any last questions at all, folks, getting through this one? Okay, so this one ended in just saying what the decomposition is. Typical thing we're going to do for an exam question is actually find the distance from y to the subspace w. That would just be the length of this vector z, like we did in the prior notes. So for pretty much the last problem in the class, there's one other question, but it's kind of a short one. The last major problem in the class is about the best approximation theorem, but really it's just a consequence of the orthogonal decomposition theorem that we just used. It tells us if you pick any random vector y in a subspace Rn and compute y hat is the projection onto some other subspace W of y, then y is the closest vector to W in the sense that it does this. The distance between y and an orthogonal projection, y hat, is going to be strictly less than y minus v for any other vector v and w, and that's a strict inequality. So this minimizes the distance, but that's just what this picture is telling us right here. The projection onto a subspace W of vector y, in other words, y hat, has a minimum distance from the vector y to a subspace W. Because that distance is at a minimum, and there's a unique answer to this, that's what the best approximation theorem tells us, it means this problem is well defined. We can calculate the distance from a random vector y to a subspace W, really in the same exact way that we did in the last section note 6.2. The only difference is the dimensions of our subspaces might be higher, and so computing Z is going to be maybe slightly more work, but same exact formulas as we've been using all along. So that's the brand new setting. This will be our last question for the day, last full problem. Example 3 is really more about connecting the notes to 6.4, the Gram-Schmidt orthogonalization process. So another big massive hint on the final exam, it'll be this one. This is the last question on the final exam. Not exactly the same numbers, but the same sort of question. We'll be given two random vectors, v1, v2. The ultimate goal is to compute the distance from the vector y, the third vector provided here, to a subspace, this one, where it spanned both v1, v2. We're already told it forms an orthogonal basis, so that means we can use the orthogonal decomposition theorem and find the best approximation to this vector y. But that's just new words for the same old object. The best approximation is just y hat. So this theorem 9 isn't really, again, anything too new. It's just focusing more on this geometry, what's providing for us, and how it gives us the distance. So when you see best approximation, think in your mind, that's just y hat again that we're calculating. So we'll take for granted that v1, v2 really forms an orthogonal basis. It looks very plausible. And that's a fast dot product. That'd be 4 minus 2. That's a negative 6 plus 0 plus a positive 6 does come out as 0. So it really is an orthogonal basis. So that means computing y hat would make sense. This formula only works for orthogonal bases. It'll be v1 times y over v1 dot v1 times v1 plus v2 times y over v2 dot v2, rescaling v2. So really the last question on the final exam is pretty much like example 1, except it's going to end on saying what the distance is, the very last part. So let's do our scratch work carefully over here on the margin for these scalar values. v1 dot y. So I'm looking at this vector v, this vector y. It's going to be 3 plus 2 minus 1 plus 26. And then the denominator, v dot v, rather v1 dot v1, is just the square of these components summed together. So it's going to be 1 plus 4 plus 1 plus 4. So this is altogether 30 tenths coming out as a 3, and that's nice and convenient. That just feels right. But keep in mind, fractions are possible. If you get a fraction, doesn't mean you're doing anything wrong, like in the last problem. It's just convenient this time, 3 times v1. Then we just do it all over again. v2 dot y over v2 dot v2. So first take this vector y dot product with v2 to fill out the numerator. That's going to give us negative 12 minus 1 plus 0 plus 39. Then v2 dot v2 is 16 plus 1 plus 0 plus 9. So this is altogether, let's see, negative 13 plus 39. So we get 26 in the numerator, and the denominator is 26 as well. That's ultra convenient, so it's plus 1 times v2. So slightly nicer linear combination to work out this time. We have to compute the entirety of y hat to get essentially what we see here in this figure, except we're in R4 rather than the suggestive R3 here. It's the same sort of mental picture, just a higher dimensional space. So first 3 times v1 is going to be 3, negative 6, negative 3, positive 6. Plus v2 is just negative 4, 1, 0, 3. gives us finally the vector y hat we're going for in this picture. It's a -1, -5, -3, 3. Now next, we're going for the vector z, but that's just going to be y minus y hat to get it. Oh, absolutely. Thanks for spotting that. So 9 down below. I appreciate all the help with the arithmetic. That's kind of the worst part about this, missing a number. So with that 9, the rest of the work should go smoothly. Other questions so far or comments? Okay, now to get the distance, all we need is the vector z, the component that's in the orthogonal complement to w. Like all the other formulas, it's going to be always y minus y hat in that particular order. So the original vector y was 3, -1, 1, 13. Minus y hat is minus -1, -5, -3, and 9. So this comes out as finally, let me know if my numbers go sideways on this again. This is 3 plus 1 for a 4, -1 plus 5 for a 4, 1 plus 3 for a 4, 13 minus 9 for a 4 as well. Kind of random looking, but that's just 4 times 1, 1, 1, 1. And now to get the distance, we just need to find the length of that vector. Let's put this on the next page. So here's the end of the problem. So if you see this as a final exam question, and you will, it's the last problem, that's for credit. Really, this is the process. It's just doing orthogonal projections in a higher dimensional space, computing a vector difference to get the orthogonal component of y, and then just finding the length of z is where all the process will end. So the distance from y to w is now just the length of z. And that's really fast. It'll be the absolute value of 4 and the square root of 1 squared plus 1 squared plus 1 squared plus 1 squared. So that goes quip. We get 4 root 4, so that's 4 by 2. And this one comes out as exactly a distance 8. There's no way I would have been able to tell that just by looking at these vectors. They are not easily plotted because we're in 4-dimensional space. But if we extend our same ideas using the best approximation theorem, we knew that the vector y hat is the closest vector to the given vector y. So calculate the distance between them. That's what we did down here for that distance. And this is our notion of distance from a vector to some other subspace in higher and higher dimensions. But we did it, folks. That's pretty much the last topic of the course. Any questions or comments getting through this one? Okay, well, this is where the notes basically end. There's one more question here, but really it was a set of questions. It says that show that U1, U2 forms a basis. But if you take the dot product of U1 dot U2, we get 0 minus 5 plus 0 plus 0 equals -5, which is not 0. It actually still forms a basis because these are linearly independent, not being multiples of each other, but it's not an orthogonal basis. So we can say U1 is not a multiple of U2, and so U1 comma U2 is linearly independent and so, well, that's half of a basis, but W is the span of U1 and U2, which is the other half. So we can say, and so is a basis. So that's problematic though, because of this part right here. It was not equal to 0, which means U1 comma U2 is not an orthogonal basis. So that's an issue with the next part B down here. We can actually calculate this distance, but not really from scratch with what we're given. If we don't have an orthogonal basis, it means you cannot do this step. You cannot find the vector projection using this formula from scratch. The vectors are orthogonal in the very first place. Everything that you try to do here comes out wrong, which is really unfortunate. And so that's the problem with part B. We can calculate the distance of this vector to this subspace, but we cannot use theorem 8, the orthogonal decomposition theorem. So it turns into a harder problem. But here's how you solve it. This is what we would have done if we didn't have a fire alarm. We would have gone to the Gram-Schmidt orthogonality process section. This is now modern linear algebra in the sense that this technique is less than 100 years old. I think it was discovered in the 60s. I have to refresh on that. It was found independently by Gram and another mathematician, Schmidt. So we call it the Gram-Schmidt process. And what it does is this. It looks really awful, but if you practice this, you'll find not too different from what we did in section 6.3. The only difference is you're building a basis. It builds from any random set here that is a basis already. Like the U1, U2. It's not an orthogonal basis though, but we can fix that. We can find a new basis that still spans W, but suddenly becomes orthogonal, so we can solve part B. It's like a cookbook. This is the whole process for finding a new orthogonal basis that will be a basis for the original subspace W. So that's what we would have done if we had enough time. If you decide to work through this section 6.4 because you have a little bit more extra time, you're all caught up on homework, I'll solve these notes so you can see how it looks on paper. And I'm going to ask an extra credit question, the actual last question of the final exam. That's something along these lines. So this one is officially the last question of the semester. That's 4 credit on the final exam. And the extra credit one just goes a little bit beyond. Well, we did it, folks. This will be our stopping point for today. When we come back next class, we're just going to be doing review problems for the final exam. But any last questions or comments at all, folks, before we call it a day? Okay, well, thanks for the hard work, everyone, on getting through the course. Thanks for everyone's helpful eyes on letting me know when Constance went sideways. There was quite a few of those opportunities that happened. When we come back Thursday, I have a set of problems that I'll go through after taking questions. But if you have any particular questions you all want to start with, whether it's homework questions, old exam questions, or else otherwise, let me know and I'll be very happy to start off with your questions. And if you'd like, you can even just email me your questions and I'll take a look at that email before class on Thursday and make sure we answer those questions as well. Otherwise, I'll be going through this document, which is a pretty big set of problems that we'll do for our review. And anything I don't solve here, I'll still finalize the solutions, just like with the 6.4 section. But have a great afternoon, folks. We'll get through one more day, and then that's it for the 15 weeks. Have a great afternoon, folks. Thanks, and here's this back for you. Thank you. Thanks. Here you go.
Extra credit question. Do you care about like the work or just the answer?
For on the 6.4,
Yeah.
I would care about the work, but if you're showing kind of the right process and you get the right answer, maybe you didn't show all the steps. I'm not going to be super critical on that.